Good evening. I apologize for the fact that we're only 5 minutes late. I had planned on more, but that's the way it goes. If somebody comes up to you at a party and asks you, what are neutrinos good for? Here's one thing you can tell them. Our sun generates its power output through a chain of fusion reactions that begin with this one, the fusion of two protons to make a deuteron, a positron, and a neutrino. Now here are the intrinsic spins of these particles, and you see that if we were to take the neutrino away, then angular momentum could not be conserved because it would try to go from an integer value to a half integer value. That's a problem. That means without the neutrino, this reaction wouldn't occur. And the entire fusion chain, which begins with this reaction, wouldn't get started. So the sun wouldn't have any power output. Instead of looking like that, it would look darker. In fact, much darker. So that's one of the things you can tell them. Now that the party's over, we're going to get serious. Neutrinos and photons are, by a long shot, the most abundant elementary particles in the universe. They're about 1 billion times more abundant than electrons, neutrons, protons. They have comparable numbers, and there are about 340 neutrinos per cubic centimeter in the universe, everywhere, like here. The neutrinos, as we just said, are spin a half. They are, of course, electrically neutral, and they are leptons. The only known forces that they experience are the weak force of the Standard Model and gravity, which has the consequence that it's very difficult to study neutrinos. However, we do know that their weak interactions are successfully described by the Standard Model. In addition, in just the last 12 years, there's been a revolution in having been discovered that neutrinos have non-zero masses and that the leptons mix. These discoveries came about from the observation that neutrinos can change from one flavor to another. This is the phenomenon referred to as Neutrino Oscillation, and so I'm going to begin these 2.5 hours of chit-chat with a discussion of the physics of neutrino flavor change. What is oscillation? What is neutrino flavor? What does it mean for the flavor to change? What does it imply? There are at least 3 flavors of neutrinos, 3 that are known: the electron neutrino, the muon neutrino, and the tau neutrino. We will define these flavors in terms of what the W does when it decays leptonically. A W can decay leptonically into an electron, a muon, or a tau, plus an accompanying neutrino. We will define the new E as the one that comes together with an electron, the new mu is the one that comes with a muon, and the new tau is the one that comes with a tau. Now, as far as we know, if you have a neutrino born this way, for instance with a muon, so it's by our definition a muon neutrino, and it quickly interacts in a detector before it has time to change into anything else, it never creates a charged lepton except that the charged lepton has the same flavor as the one with which the neutrino was born. If a neutrino is born with a muon, then when it interacts quickly, it makes only another muon. The new mu makes mu, the new E makes E, the new tau makes tau. So far as we know, if I use this notation, alpha referring to flavor, E or mu or tau, is anybody blocked by this box? Sort of iffy? Bye-bye box. All right. I'll use alpha, beta to refer to E, mu, or tau flavor. So new alpha can be a new E, new mu, or new tau. L of flavor alpha means a charged lepton of flavor alpha. The charged lepton of flavor electron just means the electron. The one of flavor muon is the muon, and the one of flavor tau is the tau. So far as we know, when the neutrino of flavor alpha interacts to make a charged lepton, that charged lepton is always of the same flavor as the neutrino. Nu E makes only E, nu mu only mu, and so forth. On the other hand, yeah, and by the way, interrupt, ask questions, point out the obvious errors that I am making deliberately as a plant to see if you point them out.
Is it possible to create a very clean muon neutrino beam then, so you can be sure that it isn't some...
That's a very good question. It is possible. Is it easy? No. Does anyone do it now? No. So the way we make muon neutrino beams usually is in pion decay, and there is a roughly 1% nu E contamination in such a beam. Does that create a problem? Yes. But we have ways, proposed ways of making pure beams in the future. I will get there, roughly at 11:30. Incidentally, I'm going to try to vote very hard to end on time because I have another talk tomorrow morning. So you're safe. If neutrinos have masses, and if leptons mix, then you can have a scenario like this, in which a neutrino is born together with a muon in pi decay, like I just mentioned. So it is by definition a muon neutrino. If this is a muon, then this is a muon neutrino. And now you send it on a long journey, like from here to the other end of the Earth. In such a long journey, the neutrino does have time to change its character. It can then interact in a detector placed on the far side of the Earth, making a charged lepton, and you can have an event in which this charged lepton is not of the same flavor as that one. For instance, it could be a tau. Now, since it is only tau neutrinos that make taus, what that means is that during this journey, the muon neutrino has changed into a tau neutrino like this, and this is the phenomenon which, for reasons that will become obvious, is called neutrino oscillation. It is the change of neutrino flavor. And the last decade has brought us really very convincing evidence that such flavor changes do occur. As we'll see, these flavor changes require non-zero neutrino masses. That means that there is some spectrum of neutrino mass eigenstates, nu1, nu2, nu3, maybe more, and we'd like to determine what this spectrum is. As we'll also see, neutrino flavor change requires leptonic mixing, and what that means is that the neutrinos that we started out talking about, nu E, nu mu, nu tau, each of which is born with the charged lepton of the same flavor, are not these mass eigenstates, but instead, each of these neutrinos of definite flavor is a linear quantum superposition of the mass eigenstates like this. I will use a Greek subscript, as I've already indicated, to refer to the neutrinos of definite flavor, nu E, nu mu, or nu tau, and a Latin subscript, I or J, to refer to a neutrino of definite mass, a mass eigenstate. The coefficients in this quantum superposition are the elements of what's called the leptonic mixing matrix. That matrix is a leptonic analog of the Kobayashi-Moskawa-Kabibo quark mixing matrix. This one is referred to as the Pontecorvo-Maki-Nakagawa-Sakata matrix in honor of the leptonic mixing pioneers. We know that there are at least 3 different neutrino flavors, nu, E, mu, and tau. That means that there are at least 3 mass eigenstates, because these are orthogonal states. They have different flavor, and out of 3 orthogonal vectors, I can certainly make at least 3 orthogonal vectors. Nu1, nu2, nu3. The mixing that we just spoke about is easily incorporated into the standard model description of the coupling of the leptons to the W boson. Before mixing, what the standard model says is that here is the coupling. It couples the neutrino of flavor alpha only to the charged lepton of the same flavor, corresponding to the experimental fact that I mentioned before, that when a neutrino of flavor alpha interacts, it makes only a charged lepton of flavor alpha. This is the semi-weak coupling constant. The L reminds us that the weak currents are left-handed. What else? W is obviously the W boson. To incorporate mixing, all you do is you replace the neutrino of definite flavor by the linear quantum superposition of mass eigenstates that we spoke about before. And now this takes mixing into account. Now, there are no neutrino masses in the standard model. When the standard model was written down, it was assumed that neutrinos have no mass. No mass was known at the time. Now that we know that they do have non-zero masses, we have to try to understand those in some way that goes beyond the standard model. If neutrino masses are described by the most straightforward extension of the standard model, and there are no new leptons beyond the ones I've been talking about, E, mu, tau, nu 1, nu 2, nu 3, only 3 of them. If that's the case, then the amplitude for a W to decay into leptons, after which the neutrino makes a lepton of a different flavor than the one with which the neutrino was born, is like this. First of all, it is the amplitude that this neutrino born with this charged lepton of flavor alpha is in particular the mass eigenstate nu I. Looking up at the Lagrangian, the term which makes a neutrino is this term. Remember that a quantum field like this one annihilates the particle that bears its name and creates the antiparticle. So the field that makes a neutrino is nu bar. Well, the amplitude that nu alpha is actually nu I is obviously u alpha I star, apart from this overall g over the square root of 2, which doesn't matter and I won't include it. So here's that amplitude. That has to be multiplied by the amplitude that this nu I, when it interacts in the detector, makes a charged lepton, which in particular has the flavor beta. The term in the Lagrangian to make L minus is over here. And the amplitude that that L minus is of flavor beta, if the incoming neutrino is nu I, is obviously u beta I. That's this factor. Because neutrino masses are very small, if you have a sequence of processes like this, you make a neutrino and then quickly it interacts, no propagating, to make an L beta, you're not going to know which mass eigenstate was involved. So the amplitudes for them, this product for each I, have to be added coherently. That's this sum. This sum is nothing but the dot product between the alpha and the beta rows of the mixing matrix. If that mixing matrix is unitary, then that dot product is the dot product between two different columns, or two different rows in a unitary matrix. That's 0. On the other hand, if beta is equal to alpha, it's the square of the vector which represents one row, and the square of one row of a matrix that's unitary is 1. So this is just delta alpha beta. If the standard model describes neutrino masses by its most straightforward extension, and if there are no new leptons, then the mixing matrix is unitary. I won't prove that, but it's true. Then this piece of arithmetic follows, and in correspondence with what we seem to see experimentally, if a neutrino is born with a charged lepton of one flavor and it quickly, without propagating, makes another charged lepton, that charged lepton has to have the same flavor as the one with which the neutrino was born. the basic meaning of the mixing matrix? Going back to the Lagrangian and looking in particular at this term, apart from this overall factor, the mixing matrix element U alpha I is nothing but the amplitude that when an incoming neutrino emits or absorbs a W boson, and it is nu I, it makes the charged lepton L alpha. So pictorially, the amplitude for nu I to make L minus alpha by emitting or absorbing a W boson is just G over the square root of 2 times U alpha I. That's what U alpha I is. It's the amplitude for this vertex. You can write the 3 by 3 presumably unitary matrix in this form. So the E row of U, this row, by example, is just that linear combination of neutrino mass eigenstates nu1, nu2, and nu3 that couples to an electron. Namely, the linear combination of neutrino mass eigenstates that couples to an electron is UE1 star nu1 plus UE2 star nu2 plus UE3 star nu3. And it's stars because that's how I happen to have defined the matrix. And some of you may have noticed that here when I plugged that in, I didn't have a star. That's not a mistake. If some state is a certain linear combination like this of other states, then the corresponding field is the same linear combination of the corresponding fields, except that there's no star there. And you all know that, but you don't know that you know that. So hopefully you'll be able to see this even though these lights are not on. The pi plus state is this linear combination of pi x and pi y. I trust most people know that? Yes? The field pi plus is the operator which, acting on the state pi plus, produces the vacuum, the ground state. Not 0, but the state 0.
Would you mind using a different color?
Only by going to the other blackboard can I do that. You can't see. It's too dark.
I have difficulty. Should I remove?
Will that help?
Yeah.
Okay. Oh, I can see it's quite faint. Now, which operator annihilates that state? The operator that annihilates that state is pi x minus I pi y over the square root of 2. The square roots of 2 combine to make a 1/2. Pi x annihilating pi x gives the vacuum. Minus I times plus I, pi y also gives the vacuum. Twice the vacuum over 2 is the vacuum. If I had a plus sign here, I'd have plus I times plus I. I'd get which is not the right answer. As this illustrates, if you have a complex coefficient in a state, you have to have the complex conjugate of that coefficient in the field that annihilates that state. And it is for that reason that there is no star here. This is an aside. It has nothing to do with neutrinos. And now, before I go on, I think we're going to make use of it. So I'm going to copy this Lagrangian and put it on the other board using a different color. You probably won't be able to see it anyway, but I mean, not you, we, all of us, but I'll turn on the lights when we need this. So the Lagrangian, this is much better, no?
Yeah, beautiful.
Ah, yes. The Lagrangian is something or other minus g over the square root of 2 times the sum over all the flavors and all the mass eigenstate neutrinos. L alpha bar gamma lambda U alpha I nu I W lambda minus plus the second term is of course just the Hermitian conjugate of the first, but it is useful sometimes to have that written out explicitly. And I think now we have the ingredients to talk about the physics of oscillation. So if you'll excuse me for just 1 second while I change the reel.
If you say that this mixing matrix is only unitary for up to 3 families, wouldn't you already know?
No, I said more than that. I said if the without saying what I was saying, what I said was if the standard model is extended in the most straightforward way to include neutrino masses, then the mixing matrix is, and if there are no new leptons, then the mixing matrix is unitary. Now, go ahead and continue.
My question was tackling the second part. If you assume there are more leptons, I understand the mixing matrix would not be unitary anymore, or you cannot prove it at least.
If there are additional leptons, then probably there is a mixing matrix which is unitary, which includes those additional leptons, but that mixing matrix is not accessible, or it may not be accessible experimentally, and the part of the bigger than 3 by 3 mixing matrix that is accessible experimentally, that is not unitary.
But overall, you would still...
Overall, there is something which is unitary, but the experiments that you do may not reveal that that's the case, so it will look to you like you're dealing with a 3 by 3 non-unitary matrix.
Thank you.
You're welcome. So now here is a theorist's eye view of a neutrino oscillation experiment. We have some source of neutrinos. Through W exchange, it emits a charged lepton of flavor alpha, a muon for instance, plus a neutrino. The neutrino goes down some beam line, and then it hits a target in a detector, and it makes, again by W exchange, a second charged lepton, for instance a tau. The electric charges here are not important for the moment. We will come back to that. What matters at the moment is just the flavors, alpha and beta. Now, since it is by definition a new alpha which is emitted with L alpha, and since the only neutrino flavor which can make L beta is a new beta, this experiment is what would conventionally be called a new alpha to new beta oscillation experiment. On the other hand, if neutrinos have non-zero masses, Then nu alpha is a superposition of those neutrinos of definite mass. And so in the mass eigenstate basis, what goes down the beamline is one or another of those mass eigenstates nu I. And because the masses are so small, we're not going to know. We're nowhere near being able to make the measurements that would tell us which mass eigenstate went down the beamline. As a result, just like in the double-slit electron interference experiment, the contributions of the different mass eigenstates have to be added coherently with one another, and consequently the amplitude for nu alpha to go to nu beta is a coherent superposition of the contributions of the various mass eigenstates nu I. Now, the contribution of a particular mass eigenstate nu I has several factors. First of all, there is the probability amplitude that the neutrino made with L alpha was in particular the mass eigenstate nu I. Well, we have here the Lagrangian. We're making an L alpha plus, so that's this term. No, this absorbs L alpha. This absorbs L, no. This absorbs, no, this absorbs L alpha minus. That's right. It's this term. So the amplitude is simply U star alpha I. Once the mass eigenstate gets to the detector and it makes charged lepton L beta with that charge, that's this term with alpha equal beta. So the amplitude is U beta I. Finally, there's some amplitude for this neutrino to propagate. The arithmetic of getting this alpha is very trivial, but conceptually it is very, very tricky, and people still argue about it. They've been doing that. This is broadly agreed to. It's not just me. The amplitude for nu I to propagate from the source to the detector over a distance L, if the beam energy is E and the mass of nu I is mi, is this phase factor. Okay, now this just repeats that. It says the amplitude for nu alpha to go to nu beta is this coherent sum, and now taking it out from the picture, that's the amplitude. It's this simple expression. And if you now take the absolute square of this amplitude to get the probability, and then you make some sneaky use of the assumed unitarity of the matrix, you can write the answer in this form, where fancy R and I refer to the real and the imaginary part of what follows. And delta m squared ij is just the difference between the squared masses of nu I and nu j. All right? Now, if you go back and you do look at the electric charges that we started with, you will see that we have been talking about a neutrino rather than an antineutrino, should there be any difference. There may not be a difference, as we'll discuss. But if there is a difference, we've been talking about a neutrino. Because a neutrino and a negatively charged lepton, like an electron, are defined to be leptons. An antineutrino and a positively charged lepton, like a positron, are defined to be antileptons. And if lepton number is conserved, then the neutral thing which can make an L minus is a neutrino, not an antineutrino. And the neutral thing which is born with an L plus from a W, which is not a lepton, is again a neutrino, not an antineutrino. So we have been talking about neutrino propagation. To talk about antineutrino propagation, you don't have to repeat the whole thing. You can make use of CPT invariance, and in fact our formalism has already assumed that because we used that standard model Lagrangian. This comes from the standard model, which is a local relativistically invariant quantum field theory. Any such quantum field theory is automatically CPT invariant. That's the CPT theorem. Now, suppose you want to calculate the probability not for nu alpha to nu beta, but for nu alpha bar to nu beta bar. The CPT mirror image of this process is nu beta going to nu alpha. C, charge conjugation, just replaces a particle by its antiparticle. In the case of neutrinos, the neutrinos that are given to us by nature to study are always left-handed. The antineutrinos, the things we call antineutrinos, are always right-handed. The difference between a left-handed and a right-handed thing is parity. So to go from what's called a nu alpha, a left-handed particle, to what's called a nu alpha bar, a right-handed antiparticle, you have to apply not C but CP, because you have to reverse the spin. Finally, we apply T, and that reverses the direction of time, so instead of the arrow pointing this way, it points the other way, or in other words, we interchange alpha and beta, final and initial state. So this is the CPT mirror image of that, and if nature, as we assume, is CPT invariant, then these two probabilities have to be equal. This probability is the probability we just derived, I just repeated it here, but with alpha and beta interchanged. And we see that when you interchange alpha and beta, all you do is you replace u by u star. So if CPT invariance holds, the probability for this process is the same as the probability for the unbarred process with the same initial and the same final flavor, but with u replaced by its complex conjugate. So I just do that. The probability for the bars is the same as before, but of course the imaginary part changes sign, so there's a minus sign here. Now, since these two processes, as we said just a minute ago, are CP mirror images of each other, this is the CP mirror image of that, this is the CP mirror image of that. If there should be a difference between the probabilities for these two CP mirror image processes, that would mean that there's a violation of invariance under CP. So complex phases in the mixing matrix lead to CP violation in neutrino oscillation through this imaginary part. Okay, now I want to write that one down too, because we're going to be using it. Can you see the red from over there? Because it's dark. I can't see it from here. I don't know how you see it from. All right, P, nu alpha goes to nu beta, or its antineutrino equivalent is delta alpha beta minus 4 a sum on the mass eigenstates, real part of u alpha I star. You can tell by the fact that I'm not looking that I must have encountered this formula a few times before. Plus, or for the case of the antineutrinos, minus sum I greater than j, the imaginary part of the same product of U matrix elements times the sine not squared L over 2e. Now, there's a bunch of comments I want to make about that formula.
The comment you just deliberately suppressed the factor 2 in front of the imaginary part.
Thank you. Suppressed is a very kind word for it. That too isn't going to matter, but it may as well be right. Just 2. Okay. First, suppose neutrinos were massless. Then in particular, all of these mass differences would be 0. All these sign functions would vanish. This probability would collapse to delta alpha beta. So, if the probability for new alpha going to new beta with beta different from alpha is non-zero, for which you need these other terms, that tells you that the neutrino masses, at least some of them, must be non-zero. So the first implication is that flavor change implies non-zero neutrino mass. And that's the most important thing about this formula. That's the big deal. The observation that neutrinos really do change flavor taught us that they have non-zero masses. Second point. Suppose there were no mixing. What that would mean is that when W the same neutrino mass eigenstate. Not sometimes nu 1, sometimes nu 2, sometimes nu 3, but always nu 1, say. And when it decays to a different charged lepton flavor, beta different from alpha, this is again always the same mass eigenstate, but a different one than over here, nu 2, say. Consequently, if there is no mixing, a product of U matrix elements involving the same I, but different alpha and beta, would be 0. If I go from here to there and I change alpha into a different beta, this new I has to be, in the absence of mixing, a different new J. So this product would be 0, and 0 here too. So once again, the oscillation probability would collapse to delta alpha beta. Consequently, if you see an actual change of flavor from one alpha to a different beta, so that this probability is not delta alpha beta, that tells you that there's non-trivial mixing. Third comment. One can detect neutrino oscillation in 2 ways. One way is to build a beam of a known flavor, like muon neutrinos, and let's say we have developed a technique for making a pure nu mu beam. And then you observe in this beam a flavor that wasn't there at the beginning, like an electron neutrino. That tells you that flavor has changed. And that, for obvious reasons, is called an appearance experiment, appearance of a new flavor. The other thing you can do is you can make a flux of neutrinos of a certain initial flavor, like nu mu again. And if you know just how big that flux is, then you can look to see if some of it disappears, presumably by oscillating into other flavors. A practical way to do that is you have 2 detectors. one that's very near the source before the neutrinos have a chance to oscillate, and one that's much farther away. And then you compare the new mu fluxes in those two detectors. If they're not related to one another simply by 1 over distance squared, that's a disappearance. So this is called a disappearance experiment. Fourth comment. I have written factors like this in the form delta m squared L over 4e, but I have been suppressing explicit factors of h bar and c, taking them to be 1. If you insert the missing factors, then this expression is really that expression. And then if you insert the known value of h bar c, which everyone knows is approximately 200 MeV Fermi, and that's about all you need. This becomes this expression, 1.27 delta m squared measured in electron volt squared, the distance between source and detector measured in kilometers, and the beam energy measured in GeV. Now, this wiggly factor, which is really this wiggly factor, is going to become appreciable when the argument in the square bracket becomes an appreciable fraction of 1, or pi over 2. Typically, when you do an experiment, it is characterized by a certain typical distance of travel, L, and a certain typical beam energy, E. And so your experiment has a certain L over E. Your experiment will be sensitive to delta m squareds all the way down to the inverse of L over E, so that this product is of order 1. So, for example, if the beam energy is 1 GeV, which is typical for oscillation experiments, if the distance is the diameter of the Earth, which is what it is for atmospheric neutrino oscillation experiments, then E over L in these units is 10 to the minus 4 because the diameter of the Earth is about 10,000 kilometers. And consequently, your experiment is sensitive to delta m squareds all the way down to of order 10 to the minus 4 electron volt squared. Really very, very tiny splittings compared, let's say, to the electron mass or any heavier particle. So what has happened is that through the quantum interference effects which give rise to these oscillations, neutrino oscillation is sensitive to very tiny mass splittings. You just have to make L over E big enough so that this phase becomes of order 1, even though the delta m squared is a very small number. Next point, an obvious point. The probability for neutrino to change flavor oscillates as a function of L over E. That's the reason this thing is called neutrino oscillation. It actually is supposed to have this behavior and has been observed to have that behavior. And incidentally, the reason that the variable with respect to which this oscillates is L over E and not L times E or some L without the E or whatever, is that neutrino oscillation is something that the neutrino is doing by itself. What the neutrino does depends on how much the clock has advanced in its own rest frame, the proper time that has elapsed between production and detection. Apart from a constant, if the neutrino travels a distance L in your laboratory frame with an energy E in your laboratory frame, then the proper time that has elapsed in its own frame is L over E. That's why the variable is L over E and not something else. And showing that oscillation actually depends on L over E, showing experimentally that it depends on L over E and not something else, is one way of telling yourself that oscillation is something that the neutrino is doing by itself rather than as a result of interacting with matter through which it may be passing or something like this. And this has been done too. Next point. You see that the way that oscillation probability depends on neutrino masses is by depending on the mass squared splittings, not the individual masses, not the absolute mass scale. So oscillation experiments can tell you what these splittings are between different members of the spectrum, but not how far above zero the whole spectrum is. Now, if you're a theorist like me and you want to build a theory of neutrino mass, it would help to know how big that mass is. Oscillation experiments cannot tell you. Next point. When neutrinos change from one flavor to another, that doesn't change the number of neutrinos in the beam. It's just changing their character from one flavor to another. The total number of neutrinos in the beam is still the same. And either by using this formula or by going back and using the amplitude from which this formula came, you can prove explicitly that if you sum the neutrino oscillation probability over all possible final flavors, including the original final flavor, the flavor with which the neutrino was born, that sum is 1. Or to put it another way, the probability that a neutrino changes flavor plus the probability that it does not is 1. And these formulas, it better be, right? These formulas explicitly conform to that, particularly if I include the factor of 2. On the other hand, some of these flavors into which the neutrino can oscillate from whatever it was initially could be what are called sterile. We'll say more about that later. But a sterile neutrino is one that does not interact by any of the known forces of nature, including the weak force of the standard model, except gravity. Well, its gravitational interaction with any detector you can build is not likely to be detectable. So if a neutrino becomes sterile, you're never going to see it right through the detector. They all go right through the detector mostly anyway, even if they're not sterile. It's hard enough to detect a non-sterile neutrino, but a sterile one, forget it. If you start with a muon neutrino, let's say, and the muon neutrinos oscillate into other flavors, but some of those flavors are sterile, then if you build a detector, the best your detector can do is to detect the active neutrinos, the ones that interact with the W boson. That's nu e, nu mu, and nu tau. And you can get the total flux of active neutrinos, but this total flux is going to be less than the original flux because some of the neutrinos became sterile. The total number of neutrinos has not changed, but some of them have become completely invisible. So it's going to look to you like the flux went down. Final comment. We know that there are, yes?
It would still be unitary, the whole mixing matrix and everything.
Yeah. You look uncomfortable with that. Everything is still fine.
Because that will mean that if it goes to sterile, I can also go back again.
Yes.
Well, that will mean that if you lose flux, and
You may get it back again if you move your detector farther.
because I was thinking in the end you lose all the flux.
Oh, no, 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 no. They don't necessarily all go away. Oscillation is oscillation. I mean, that's really weird. If you're focused on a particular flavor, you put your detector here, you see a certain number. You put your detector here, you see less. You put your detector here, you see more again. Ooh, look at that. That's how it works, and it's been observed to work that way. It's not just the formulas on a blackboard or whiteboard or whatever it is.
So there's no evidence for thermal neutrinos from the experimental part?
I didn't say that.
Okay. No, no.
Stick around. I'm coming back to that point,
Okay.
but about 1 a.m. We'll get there. I want to make sure we get there. I will skip other things to make sure we get there, if necessary. We know that there are at least 3 neutrino mass eigenstates and 3 corresponding flavors. However, to a very good approximation, if you're just trying to describe one experiment, it is a very good approximation to take just 2 neutrinos into account. 2 mass eigenstates, call them nu1 and nu2, so there's only one delta m squared, m2 squared minus m1 squared. And 2 flavored neutrinos, call them nu alpha, nu beta, made up out of nu1, nu2 by this quantum superposition. When you do that, the mixing matrix becomes just a 2 by 2 matrix. It's not really unitary because the real matrix is bigger, but to a good approximation it might be unitary. And the most general expression for a 2 by 2 unitary matrix that takes into account that certain phases don't have any meaning, because what I call an electron you can call e to the I 37 degrees times an electron. You can remove phases that way. The most general expression is a 2 by 2 rotation matrix depending on a rotation angle theta, which is called the mixing angle, times a matrix which has a phase in it, but this phase does not affect neutrino oscillation. And when you plug this mixing matrix and the approximation that there's only one delta m squared into this formula, it collapses to something very simple. The probability for nu alpha to go to nu beta, or the other way around, or the antineutrinos, is just sine squared of twice this mixing angle times the sine squared of this one oscillatory factor that is still left. And the probability that nu alpha does not change its flavor is just 1 minus the probability that it does. And these simple formulas have been used to describe numerous experiments, and I'm going to copy them on the blackboard also. Whiteboard. Okay, so this is 2 nus.
You expect that oscillations can collapse into effective 2 flavor interactions. Is that general, or is that related to the fact that some angles or some mass differences are larger than others?
The latter. I would have put it the other way around. Some are smaller than others. Exactly so. This collapse is a piece of luck. It comes about actually because of 2 things. One of them is what you just said, and the other is, suppose the spectrum, as we'll see in a while, looks like this. There's one small gap and then there's a much bigger gap. If I do an experiment that is just adequate to see the big gap, it's not going to be able to see the small gap. So for this experiment, these 2 neutrinos look like they're degenerate. They look like one neutrino. So this looks like a 2 neutrino spectrum, even though it's not. That's the other piece of luck. Because of those 2 things together, we have this possibility. And I mean, it's not just that the formula is simple. It's that it's a function of two parameters, just two instead of this, which is relatively a mess. It's, and the other piece of good luck is that those delta m squareds, although they are very small, they were big enough to be observed experimentally, and you know, that's lucky. Okay, so now I have to change the reel again. Yes, well, why don't we just do this? Now, I mentioned when talking about the propagator from the source to the detector that people still argue about the quantum mechanics of neutrino oscillation. And recently there was some excitement when it was suggested that everything I have said so far is wrong. Let's talk about neutrinos made in pion decay. Most of those decays result in a muon in a neutrino. And for a given parent pion energy, for example, the pion at rest, the neutrino and the muon with which it was produced are kinematically entangled. That is to say, their kinematical properties are correlated with one another because of energy momentum conservation. The energy of the muon is going to depend in the pion rest frame on how much this neutrino weighs. So it's going to depend on which mass eigenstate was emitted. That's what you mean by quantum entanglement. You have a decay into two particles. They go out in opposite direction. The properties of this are entangled with the property of that. They're not independent. So you can ask, when that is taken into account, which I did not do in deriving these formulas, do we still expect neutrinos to oscillate like this function with an oscillation wavelength which is defined that way, and you can just solve equating these two things, 4 pi e over delta m squared? Well, within the last year, an approach taking entanglement into account was constructed, and the wavelength that was derived for the oscillation looked very different than that usual one, like 50% different. However, that new wavelength derived by that approach is not for oscillation as a function of the distance between the source, that is to say where the pion decays, and the detector where the neutrino is detected. Rather, when looked at closely, this new oscillation wavelength is for oscillation as a function of the lab frame separation, S, between the neutrino and the muon at the time in the pion rest frame when the neutrino is detected. Now that sounds like the most ridiculous variable you've ever heard of, but it's not actually from the point of view of this approach. You're supposing you have a pion and it decays into a neutrino which goes that way, and in its rest frame a muon which goes in the other direction. They're entangled. So the natural variable is the separation between them, not the distance that either one of them has traveled alone. And at what time? Well, the same time in the pion rest frame, obviously. That's where they just came from. The pion was their parent. However, in the lab, that looks really weird. In the lab, first of all, if this pion has a lot of energy, the neutrino and the muon are both going in the direction that the neutrino is going in, so they're both going in this direction. And the separation between them is less than the source to the detector distance. And now, if you work out the relativistic kinematics, you find that the new wavelength that was derived by the entangled approach is to the usual wavelength, the one that's in here, as this new variable is to the usual variable. In other words, the new wavelength is actually physically equivalent to the usual one, but it refers to a different variable. And so it has to be bigger than the usual one by the amount, or smaller, by the amount that that new variable is smaller than the usual one. And that's exactly what one finds. So, yet another threat to the usual results has been defeated. But more threats will come. Now, without my explicitly mentioning it, we have been talking so far about neutrino oscillation in vacuum. I never talked about the neutrinos interacting with stuff while they're undergoing their journey. But any experiment that you do is going to have the neutrinos traveling through some matter or other. For example, if you use an accelerator to make your neutrinos, and then you fire them at a distant detector, because the Earth's surface is curved and the neutrinos follow a straight line, they will be traveling through Earth matter like this. Now, on the way, they will encounter electrons, lots of them. If the beam is neutrinos as opposed to antineutrinos, the new E component in that beam can exchange a W with an electron in the matter like this. If what's going down the beamline is antineutrinos, then the new E bar component can make this diagram, again exchanging a W this time in this channel rather than that one, with an electron in the matter. It's only the new E or new E bar component that can do this, because according to this formula, when you write it in the form pre-mixing, it's only the electron neutrino that couples to the W and an electron. And we don't have muons and taus in the Earth, we have just electrons. So this affects just the nu E or the nu E bar component of the beam. However, it can affect it in a big way, because there's lots of electrons in the Earth, and the coherent forward, dead forward scattering via this or that diagram leads to an extra interaction potential energy on the part of nu E or of nu E bar as it travels through matter. And how big is this extra interaction potential energy? Well, it's going to be of order the Fermi constant, because that constant measures the size of either of these amplitudes. It's going to be proportional to how many electrons there are around to interact with, so the electron number density. And the coefficient out front we cannot do by hand waving, but the standard model tells us that it's plus the square root of 2 for a neutrino beam, and minus that for an antineutrino beam. So this matter effect, because that's a plus, raises the energy of a nu E inside matter, and it lowers the energy of a nu E bar. The fractional importance of that matter effect on oscillation involving a vacuum splitting delta m squared can be gauged by this parameter that I'll call x. This is the interaction energy again, there it is. And the thing with which that has to compete is the vacuum energy splitting that governs the oscillatory behavior of oscillation. And before I change this into a sine squared function from the cosine that it was before, that was delta m squared L over 2E. So this is x. And now some comments about x. It grows with the neutrino energy, because this is in the denominator of the denominator. So the bigger the energy is, the bigger the matter importance. It is sensitive to the sign of delta m squared. What do I mean by the sign of delta m squared? Well, suppose you have two mass eigenstates and you know something from elsewhere about them. Like this one couples a lot to electrons and that one doesn't. The sign of delta m squared can tell you whether the one that couples to electrons is heavier than the other guy or the other way around. Finally, remember that this interaction potential flips sign when you go from neutrino to antineutrino. So the effective matter correspondingly flips sign when you go from neutrino to antineutrino. And if x is of order 1, the matter effect is important. If x is 100, it's very important. If x is very small compared to 1, the matter effect is negligible. There have been experiments of both kinds, where the matter was important, where the matter was negligible. The canonical coffee break hour is at 8:45. We started 5 minutes late, so maybe it's between 8:45 and 8:50. We have a few minutes. I'll keep going a short time, and then we'll break. I'm not going to take the time to tell you about the really beautiful experiments which have demonstrated that neutrinos really do oscillate, but I will summarize where we stand. We have really very strongly convincing evidence for flavor change on the part of neutrinos made by the sun in fusion reactions like the one I talked about at the very beginning. Neutrinos that are emitted by nuclear power plants and are allowed to travel a few hundred kilometers. Neutrinos made in the Earth's atmosphere by incoming cosmic rays. And there you do an experiment where you study not just the neutrinos coming from overhead, but the ones coming from the Earth's atmosphere on the far side of the Earth. So they've traveled through the whole Earth to get to your detector. Neutrinos made by particle accelerators, like the one at Fermilab, where I work, and that travel a few hundred kilometers. And there's even some evidence, to which we will return, from an experiment called LSND, which reports that perhaps the neutrinos from stop mu plus decay oscillate already when they travel 30 meters, not kilometers, meters. And there's an experiment running at Fermilab which is called Miniboon, which is supposed to confirm or refute LSND, and I will talk about what Miniboon sees later. Here there's a question, a very interesting question. There is no question. These neutrinos change flavor. So what, yes?
Just a short question on your side. So you listed the experiment about neutrino changes, flavor changes.
Yep.
Which means you're looking for your sensitivity on the delta M. Are there any observables in the standard model that like colliders would be sensitive to for direct measurement of the eigenstate of the mass?
Not at a collider.
Yeah.
Because probably not at a collider, because the masses are so small.
Yeah.
You have to, if you want to do that, you have to do something that is sensitive to very, very, very small masses, not mass splittings, but masses, which means probably you're better off at very low energies, where the energies are not enormous compared to the masses.
Okay.
I'll come back to that. So what have we learned from all the oscillation data? We know that there are at least 3 mass eigenstates, nu1, 2, and 3. 2 of them are separated by this quite small so-called solar delta m squared, and it's called that because this drives flavor change on the part of neutrinos from the sun. The third neutrino is separated from this closely spaced pair by a roughly 30 times bigger atmospheric delta m squared, which describes what neutrinos made in the Earth's atmosphere do as they travel through the whole Earth. We don't know whether the closely spaced pair is at the bottom of the spectrum or at the top. If it's at the bottom, then the neutrino spectrum would resemble qualitatively the charged quark spectrum, the positively charged quark spectrum, the negatively charged quark spectrum, the charged lepton spectrum. They all look qualitatively this way. A small gap at the bottom and a big gap at the top. For instance, the up quark, the charm quark, and the top quark way the heck up there. On the other hand, it could look like this. And if the neutrino spectrum looks like that, it would be called inverted. If it looks like the other spectra, it would be called normal. That just means it looks like the other spectra. This is an interesting question. We don't know the answer. Because oscillation experiments measure only splittings, we also don't know how far above zero the whole pattern is, the absolute scale. Now, oscillation does tell us something. Wherever, I don't know if the spectrum looks this way or upside down, it doesn't matter. Somebody is at the bottom of the spectrum. And wherever the guy at the bottom of the spectrum is, it's not below zero. So whichever state is at the top of the spectrum must have a mass squared which is no smaller than the bigger of the two delta m squares. And that means its mass must be no smaller than the square root of that number. And the square root of that number is about 0.04 electron volts. So whoever is at the top of the spectrum weighs at least that much. We already know that. Cosmology, on the other hand, gives us an upper limit. All those neutrinos in the universe affect large-scale structure on the scale of galaxies, clusters of galaxies, clusters of clusters of galaxies, and the masses affect large-scale structure in a way that depends on how big the masses are. What you can get from cosmology depends on which data you are willing to use and what cosmological assumptions you're willing to make. But for reasonable use of data and assumptions, you get an upper bound on the sum of the masses of the mass eigenstates, which is somewhere between 0.17 and something like 1 electron volt. So we have an upper bound. If the upper bound can be taken to be this more aggressive value, and if there are only 3 neutrinos looking either this way or that way, then this upper bound on the sum of their masses translates into that upper bound on whichever is the heaviest particle. On the other hand, if the cosmological bound is really just 1, then the corresponding bound on the mass of the heaviest is 0.4, something like that. So if the 0.17 can be believed, then we already know the mass of the heaviest member of the spectrum. It's something like 0.05 electron volts. It's between 0.04 and 0.07. And once you know the heaviest mass, we do know the splittings. We can now determine the lighter masses too. On the other hand, if it's this more conservative bound, then there's an order of magnitude difference between these two. Now, cosmology is wonderful, but there are known loopholes in the cosmological argument that connects you from cosmological observations on the one hand to a statement about neutrino masses on the other. So I think in the end there's going to be no substitute for an absolute neutrino mass measurement in the laboratory using the kind of technique that you were asking about. And the technique that people are pursuing most is nothing like a collider experiment. It's the opposite in some sense. You look at tritium beta decay. This is one of the beta decays with the smallest energy release of any beta decay. It's only about 17 kilo electron volts. It's not MeV. And what you measure is the spectrum of the outgoing betas, the outgoing electrons. Now, when tritium decays, the electron is accompanied by one or another of the mass eigenstates, nu1, nu2, nu3. It happens to be a nu bar because that's an electron, but the bar is not the point. It's nu1 or it's nu2 or it's nu3, and the branching ratio for making a particular nu I is the probability of making that nu I in connection with an electron. In other words, from this Lagrangian, it is the square of UEI. So there are 3 different decay modes here, one of which produces nu1 bar, one produces nu2 bar, one produces nu3 bar. And obviously, for a particular outgoing mass eigenstate, the heavier that mass eigenstate is, the less energy is left over for the electron. So the electron spectrum is going to be affected. And there are 3 separate thresholds in that electron energy spectrum. As you start with high electron energy and you move down, first you reach a point where the lightest mass eigenstate neutrino can be emitted. That's where the decay starts. As you move down further, eventually the next heavier mass eigenstate neutrino can be emitted, and there's a threshold. As you move down farther still, the heaviest of all the 3 mass eigenstates can be emitted, and there's another threshold. One finds that in the presence of masses on the part of the mass eigenstates, the spectrum that you would have in the absence of mass gets modified into this spectrum. As I said, it is the sum of 3 separate spectra. So it's the incoherent sum like this. Each spectrum has its threshold where the energy becomes low enough to emit mass mi, and there is this factor times that replacing this factor in the massless limit. Now, present experimental energy resolution is insufficient to separate those 3 thresholds. So what is measured is actually an average, a weighted average over the mass squared because that's what occurs there, of the different mass eigenstates, each one weighted by the branching ratio for emitting that mass eigenstate. And they haven't measured that either. They've just gotten an upper limit so far on it, and that upper limit is 2 electron volts. So it's down around the same place as the upper bound of 1 electron volt from cosmology, but this one does not involve any cosmological assumptions. That's the answer to your question. This is how you go about it. It's the non-collider limit. I think this might be a suitable place to break.